Okay, so what this means right here, this is a symbol for conditional probability. Do you guys know what the P means on the outside? P just means probability. So like if I was rolling a die and I said, what are the chances of you getting a 3? What's the chances of you getting a 3 when you roll a die?
1 out of 6.
1 out of 6. So if I was going to write that mathematically, I'd write it like this, look up. I'd say the probability of getting a 3 is 1 out of 6. Okay, so using that P on the outside means probability in math, or at least in statistics. Okay, so what's the probability? And what this means is it means that find the probability of A, or sorry, find the probability of B given that A already happened. So A happened first, and then we're specifically trying to find the probability of B. Okay. Example 1. 2 cards are selected in sequence from, or form, a standard deck. Find the probability that the second card is a queen given that the first card is a king, and assume that the king is not replaced. Okay, so imagine I've got a deck of cards. I'm holding it out from you like a magician. What are the chances of you pulling a king?
It's 52 or 51 cards.
52 cards in a deck. So what are your chances of pulling a king? 4 out of 52, or 1 out of 13. 1/13th, right? Does everybody understand that there's 4 kings? Okay. But that's not what the probability we're looking for, so we're not even going to write it down. We're trying to figure out what's the probability of picking a queen after you've picked a king. Now imagine that I picked the king of, Michaela, the king of, make it up, spades. Okay, so I got the king of spades right here. Can everybody see it? Okay, well there's nothing there, but okay, thank you. So, king of spades, and then I throw it away. I'm not going to put it back in the deck. And then I magician my hands out again. And this time we know the king of spades isn't in there, right? Okay, what are your chances of drawing a queen now?
4 over 51.
4 out of 51. So the answer for this problem is 4 out of 51. And the conditional part about it is what? What changed because I threw away the king?
Amount of cards.
The amount of cards. So instead of being 52, now it's 51. Okay. The table below shows the result of a study in which researchers examined a child's IQ and the presence of a specific gene. So basically, they were trying to figure out whether this gene, whether if a gene was present, whether that helped determine whether a kid was going to be smart or not. Okay, let's just look at it first of all. The kids with a high IQ, 33 of them had the gene, 19 of them didn't. Kids with a normal IQ, 39 of them had the gene and 11 didn't. What do you think? Does the gene affect your IQ? Doesn't seem to, right? It's not like it's abnormally, like a whole, like if this was 33 and 19 and then this one was like 10 and then a whole big high number over here instead, like 40, that'd be completely different. But this one's not showing that, but we can still mess with it. So, find the probability that a child has an IQ given that the child has the gene. This is a hard thing to figure out, so I'm going to do this with colors. Anybody else want a highlighter? I've got a bunch. Highlighters? All around? Ladies, highlighter?
I'm okay, I got it.
Nathan?
I guess.
What? Why are you mad about getting a highlighter? You want a highlighter?
I'm okay.
Okay. All right, so given that the child has the gene, Nathan, you sounded exactly like my 7-year-old son right there. Stop that. Okay, so we're only looking at the people who have the gene. That's all we care about. We've stopped looking at everything else, okay? So don't pick any of these numbers over here. All we care about is that the child has the gene. Now, what are the chances that if the child has the gene that they have a high IQ?
33 over 72.
Yes, so the answer to this problem is 33 over 72. So it really kind of, it focuses it just on the people who have the gene. That's what the total is just the gene people. What I want you to try right now is I want you to try example 3 with your partner. Talk to each other.
You have that, you can do the other column. 44 over 51.
So do we add 19?
Just the other column is the same thing for normal IQ.
So 11.
Okay.
I'm going to give you a hint. Look up. Given that the child has a normal IQ, so you should only be looking here.
Yeah.
You shouldn't be doing anything besides the stuff that is in yellow.
Is it, for the 5% thing, does it also work the other ways? Like would anything above 95 be unusual?
No, that's certain.
That's certain.
That's close to certain, yeah. So almost guaranteed, I guess is what you would call it. Unusual is not, it's not like a bell curve where you assume that like the extremes are unusual. It's like if I said, what are the chances that you're gonna come to school today wearing shoes?
If it's in the, okay.
Yeah, and you wouldn't say unusually every time, you know, like, because that's not unusual, it's every time. So with probability, it's not in that same way. Good question. All right, who wants to win a prize? Back team? Back team. Go ahead, explain.
So it's find the probability that the child does not have the gene.
Mm-hmm.
So then we want to look at the column where the genes aren't present, but then it says given that the child has a normal IQ. So you only want to use the column that has a normal IQ. And then there's only 11 kids with a normal IQ that does not have the gene present, and then there's 50 total, so it's 11 divided by 50.
Perfect. Does everybody understand? Okay, so the given part is the stuff that you're highlighting, and that's only the things you're going to look at. That part of your homework will be like that. Okay.